Finally, I want to address the reference implementation which has been made. This is the schematic of the Linux-based reference implementation, and it is completely based on the concepts, the architecture, and the algorithms which have been defined and developed during the Omega project here in WP5 by help of the technology-dependent work packages 2 to 4, as you have maybe heard yesterday. And it provides a proof of concept that it is reasonable to go for this approach to manage heterogeneous home networks. Another feature of our implementation is that it is portable to different platforms due to hardware abstraction layers which are already existing. For example, the proof of concept demonstration was done on a Linux-based system, but it can also be done on an FPGA platform, because there is code existing which is defining a hardware abstraction layer for data plane and for the data plane especially. So you see, maybe just to shortly address the structure on the right-hand side, you see all these engines here: QoS engine, power selection engine, monitoring engine, and now they are separated. Here we have them in Linux user space because they are performing some tasks which are not time critical. But what the data plane does, and to achieve gigabit forwarding, as Professor Kremer has pointed out, it was necessary to situate some parts, especially the data plane, in the kernel space. And also we will publish a paper on this from the implementation team, which will demonstrate how these engines have been developed and realized the InterMAC concept. So finally, I want to give you an example. Of course, it is not as good as what you have seen in reality below, but again, I want to show you how it works. Now, if you, when you have an impression of all mechanisms we have envisioned in Omega, in the InterMAC work package. So we see a heterogeneous mesh network, where there is an HTTP stream of about 27 megabits from node 3 here to node 2. It uses the Ethernet path, which is completely consisting of Ethernet from N3 to N1 over a hop which is N2. So, on the right-hand side you can see the IP throughput at N1, which is approximately 28 or 27 megabits over the time. And this what you see here is the data rate, so the IP throughput at N1 for the specific interfaces. Now we are looking currently at the gigabit Ethernet interface at 1. All the other links, which are green, are exchanging probe frames. So you know this link is available. But it's also possible to switch down, power down interfaces. For example, the wireless LAN interface here, to save energy. Simply to save energy, if you don't need it. So, now, just think that you detach the Ethernet cable, or the link breaks due to any other reason. A new path has to be established between N2 and N1. Actually, it has to be established between N3 and N1. So, in our demonstrator, it's like this, that N1 always, periodically floods the network with path requests in order to detect or explore new paths if they are available. So, in this case, the technology is switched to millimeter wave interface, which is the 60 gigahertz direct link connection you have seen below. You see, there's just a small fade of the data rate, but it can keep constant here. Now someone walks through the line of sight path, and again this interface is not available anymore. Now we have N3 has to go a completely different route. There are path requests again, and the traffic is now rerouted over an Ethernet link from N3 to N4, and here the technology is switched from Ethernet to PLC. Again, you can see the data rate on the left, on the right hand side. Now the PLC degrades. PLC link degrades somehow. PLC always has a lot of problems with other electrical devices in the home grid. For example, these adapters and computers or so on, they produce heavy background noise. And a new path has to be found. And this is now the Ethernet path and the wireless LAN path, because it is, in this case, the only one which is available. And you can see the characteristic behavior of the data rate for a wireless link here. It is, let's say, jittering around a certain mean. And finally, you can see the Ethernet link becomes available again. And in this case, M3 periodically sends out path requests and will be aware of this, that the Ethernet link will reappear because of the answers coming from N1 due to the, or N2 due to the load probe frames, and this link can be used again. And as you can see, the data rate keeps constant, and we can serve an HDTV stream over this heterogeneous network structure, which is definitely, I think, very new. So I come to the conclusion and the outlook of my talk. As a conclusion, we can say that in WP5, especially in the Omega project, we lay the technical foundation for the InterMAC. We provided an InterMAC reference architecture, algorithms and mechanisms for the most challenging tasks appearing in the InterMAC. We have developed a proof of concept demonstrator. And so, my thought is that the InterMAC is an enabling technology for the benefit of the end user, because there may be services which we cannot think of today, but they may be there tomorrow. And now the InterMAC is there, and we can do anything with it, and we can put more efficient algorithms in it. So what we have done in the Omega is we had a vision, developed a concept, provided algorithms and mechanisms based on the concept and the vision, and we finally demonstrated that it works. So we have a proof of concept demonstrator. As we have heard already tomorrow by Paul José, there's a standardization activity going on now, which is called a standard for a convergent digital home network for heterogeneous technologies. It is abbreviated by P1905.1, and it has been approved in November 2010. And I will not go into detail here because we have heard it from the direct source in the morning, but it will pick up the concept of the InterMAC, and with the help of manufacturers and consumer electronic manufacturers, it may be possible to develop an elaborated standard out of this. For future research, because I'm not from an industry company, I'm from an academic partner in the project, I'm always looking for future research opportunities. And there we have several opportunities I've listed here. For example, we need to find efficient device and network architectures. This is really an important task. Furthermore, as we have heard today, for all these smart grid discussions and so on, we need to extend the InterMAC concept from a research perspective by a wireless sensor network, to initiate the integration of smart home appliances, and to support what is called ambient assisted living, or machine-to-machine communication within the home. Of course, we only could initiate this InterMAC vision and idea in this project, and they have to be, we have to find even more efficient algorithms for all these engines in the InterMAC. For example, a path selection could look for the most energy efficient path within the home network, just to give one example. And a really, really important task is now to find efficient implementations of the InterMAC. And I think with our reference implementation, we have done a good job with this. Of course, this list is a long list and has to be continued. Here I provide you with some references. I guess maybe the slides can be uploaded to the website. So we have produced some deliverables and white papers, and they are available through our homepage, www.ict-omega.eu. And besides this, we have also produced some papers. I just selected some which provide some input for my talk here. And a complete list of papers is also available through the website. Finally, I want to thank for contributions in WP5 on behalf of WP5. So these were the partners which have been involved in the InterMAC work package. Thank you to all. It was a pleasure for me to work with you in the project, and I think we have achieved a lot here. So thank you for your attention.